So welcome everyone. I think I know most of you in the room. Oh, this one. Perfect. So I'm going to start with just giving you a little outline of things to come. So we'll talk about the guideline changes and the derivation of the aesthetic objective and the new MAC. I'll just touch briefly upon the health impacts to manganese exposure, and we'll look at the estimated impacts to Nova Scotia's public drinking water supplies. We'll talk a little bit about the recommended monitoring requirements for manganese, and Gavin will talk about manganese occurrence in Nova Scotia. So currently, manganese in drinking water is measured against an aesthetic objective of 0.05 milligrams per liter. And with the upcoming guideline changes expected to be released this fall, we're going to see that reduced to 0.02 milligrams per liter and an introduction of a maximum acceptable concentration value of 0.12, as well as they use the lowest observed effect as opposed to a no observed adverse effect. I'm not a risk assessment person, but that's just the quick and dirty of it. So from there, from the TA, they multiplied it by the average weight of, so infants and to be the most vulnerable population, and they multiplied it by an allocation factor of 0.5, so assuming that half of your exposure comes from drinking water and half from food. The period for the guideline was brought forward. Nova Scotia Environment did do a review of data that was on hand for both municipal and registered systems. And comparing that data that we do have, we looked at how many systems might be impacted by the aesthetic objective and the maximum acceptable concentration value. So let me just catch up to my statistics so I don't get them wrong. All right, perfect. So 6% of municipal systems exceeded the new MAC guideline on occasion, and approximately 13% of municipal systems exceeded the new aesthetic objective on occasion. Again, remembering this is a very limited data set, and it might not actually capture periods of time when a lake might be turning over and where we would expect to see sort of short-term increases or decreases in manganese. With respect to the registered supplies, it's estimated that approximately 20% of the supplies might be impacted. But again, they're sampling less frequently and reporting less frequently. So once you see Gavin's presentation on manganese in the province, you might be able to assume that that impact might be greater. But once we get some data following new monitoring requirements and reporting requirements, we would have a better understanding. So this sort of outlines the general recommendations by Health Canada for manganese monitoring. For groundwater sources, they're recommending semi-annual monitoring for all wells within a well field because they've seen evidence of changes in concentration in a well field. And for surface waters, they're recommending quarterly sampling and weekly in the summer and fall. Weekly in the summer and fall, that seems to be a little bit onerous, and we feel that most municipal systems probably have a good sense of, especially surface water, the certain times of year where they're going to see those quick decreases or increases in manganese. So an approved sampling plan should reflect when they typically see those seasonal changes. Now, if there is a good baseline of data showing that manganese concentrations are below 0.02 milligrams per liter, they can then apply to the department for consideration of reduced sampling. With respect to process monitoring, that would be on a required basis. And so, again, that would depend on the type of treatment and the type of manganese occurrence in their source water. However, for that, colorimetric analysis would be acceptable. And for those weekly samples, colorimetric analysis would also be accepted by the department, as long as they're validated with quarterly samples done by an accredited laboratory. Now, with respect to the distribution sampling, it's recommended that minimum sampling requirements are done quarterly for the treated water, so at the treatment plant or near the treatment plant, and then throughout the distribution system. So not unlike what most utilities are doing for their corrosion monitoring. However, they are recommending that event-based manganese monitoring be conducted following any kind of hydraulic disturbance, so a main break or seasonal flushing, as well as any kind of chemistry change possibly related to lapses in process control or changes to your typical treatment process, as well as during any major discolored water events. And with those event-based monitoring, they do recommend that you co-sample with other metals and not just manganese, and potentially other water chemistry parameters. So now that manganese does have an MAC, there will be reporting requirements and notification requirements to the Department of Nova Scotia Environment, and those are not unlike the current requirements for reporting on chemical parameter exceedances. So if a sample is found to have exceeded the MAC, the owner is required to report that to Nova Scotia Environment and follow up with confirmatory sampling. And if the confirmatory sample also exceeds the MAC, then the owner is required to do a cause investigation. So it may be that the source water quality changed suddenly and the process control couldn't keep up, or they may be seeing diminished treatment efficacy. It could also be related to, as we discussed, distribution water chemistry changes and hydraulic changes. So depending on the outcome of the cause investigation, if it's a quick fix, the utility will go ahead and do that. However, if it's something that requires a long-term solution, a corrective action plan should be submitted to the department for approval prior to implementation. So I'm going to pass it over to Gavin now.
Good afternoon. I'm going to speak to the impacts of the guideline changes on private well users. So as noted earlier, over 40% of Nova Scotians rely on private wells for their domestic water supply. There's no regulatory requirement for testing and treating private well water supplies, but NSE does recommend that well water is tested every 1 to 2 years, or if a change in quality is noticed. Treatment or an alternate supply of drinking water is only recommended if a health parameter is exceeded. So in the case of manganese, which was an aesthetic objective, a recommendation would not have been elicited if elevated manganese was detected in a well previously. Manganese is widely distributed in various rock types throughout Nova Scotia, and the province has a history of mining and mineral exploration for manganese for industrial usage. The metal's mainly being used as a hardener in metal fabrication. So even recently there was some exploration by a Chinese company looking for manganese, so it still it fluctuates with the demand of the mineral. Mosers Island and Beaver Bank formations are associated with the highest levels of manganese, and they are part of the Goldenville group, which is metasandstone dominated. Soil, till, and sediment throughout Nova Scotia are all sourced locally from bedrock, which has been eroded and deposited from glacial advances and retreat. So not surprisingly, superficial materials can also be elevated in manganese. So this map shows the distribution of manganese in bedrock aquifers for the province's 5 major groundwater regions. And that's the plutonic, sedimentary, metamorphic, carbonate evaporate, and volcanic. The chemistry data shown on the map comes from the province's ambient raw water chemistry database. And as you can see, the distribution of manganese in our bedrock aquifers is widely distributed. And the distribution is controlled by various factors relating to the concentration in the source rock, as well as aquifer flow and geochemistry dynamics. The median concentration in the data set actually exceeds the new AO, and the mean concentration exceeds the new MAC. So it's clearly a problem throughout Nova Scotia. So further analysis of the data set shows that the percent of samples exceeding the old AO the new AO compared to the old AO jumps from 38 to 50%, and about a quarter of the samples exceed the proposed MAC. So a further break data set by groundwater region shows that the highest exceedance rate for manganese in private wells is in the metamorphic and plutonic groundwater regions with upwards of 34 to 40%. However, the highest percent of impacted population is in the metamorphic and sedimentary groundwater regions. So in total, there's estimated about 110,000 private well users on a population basis will be affected by the new MAC. So I think I'll let Krysta talk about steps there.
All right, so as I said previously, Health Canada plans to implement the revised manganese guideline this fall, in which Nova Scotia Environment will be adopting that guideline. So from our perspective, we're going to attempt to do several public education initiatives. Not all determined yet, but there are several changes to our registered supply program that we're evaluating currently. So we'll probably release something that will reflect this and other changes as well. And this is sort of our first education and outreach initiative related to registered and municipal supplies. And we'll look for other opportunities at upcoming conferences as well to make sure that everybody understands new guideline changes, and if there's any questions or concerns in implementing it, we'll be on hand to answer those. We'll be developing a manganese fact sheet on our website, typically aimed at registered users. And
yeah, and the map I showed earlier showing the distribution of manganese in our bedrock aquifers, we plan to release that as an open file map when the new guideline is implemented by Health Canada. And we will look into the potential for developing a manganese in bedrock aquifers risk map similar to the one that we previously developed for arsenic. We'll look into that and maybe down the road publish something in terms of risk map.
That concludes our presentation.
Thanks. All right. If anybody doesn't know me, you've been lucky. If you do, we're going to talk about manganese. Who's listening on the internet? And I think some people in Newfoundland too. They wanted me to mention that since they're listening. All right. So, just like a good Law and Order episode, this topic is straight from the headlines. Manganese is a problem right now in Nova Scotia. This is a news story from Bottledeck First Nation in Cape Breton from last week. And I spent some time in the community last week, and they have a black water problem. They have a manganese problem. And I would say, with zero facts to back it up, that there is no other parameter in drinking water that drives more customer complaints than manganese or its weaker brother, iron. But manganese is the source of complaints. It's not the same as the invisible stuff that you can't see, but this is it has direct impacts aesthetically. And traditionally, the treatment for manganese has been done because of issues of black water. It's not acceptable to provide water that is or will turn black later on to a customer, and so treatment requirements have been driven by an aesthetic need, and not like the aesthetic, which I think is in the headline up there, which is really like esthetician sort of aesthetic for the CBC for that one. But now we're moving from manganese being treated because it's not cool to have that to being not regulatorily acceptable, maybe. So issues of manganese are very well known. I would say science and literature on manganese is quite old, and there's not a lot of current research. If you go look at academic papers and stuff on manganese treatment, they date back into the 1930s, 40s, 50s, and that's generally the same as treatment practice is today. There are some forms of evolving sort of research on treatment for manganese, but really the problems come through tuberculation in biofilm, dirty water issues, things that you would generally see as opposed to not see. So for the little bit that I'm going to talk about, I'm going to kind of just run through some things on treatment and then just a little tiny bit on sampling. So when thinking about how to break this up, I thought, well, what we'll do is go through manganese treatment from a surface water perspective, groundwater perspective, and not really going to touch the private or registered system, very small scale stuff, although the technologies are sometimes different for that. Photo is from the Rothsay water treatment plant in Rothsay, New Brunswick, which is a groundwater manganese plant that uses permanganate oxidation and membrane filtration. It's the only plant in Atlantic Canada designed specifically for manganese treatment using a membrane system. And it's been there since the mid-1990s. So I would consider that if you have a source with manganese and you have to do treatment, you generally would fall into one of four categories. You have, or skipping over the first one, and then if you were in no source water manganese and no need for treatment, this is not the presentation for you because it's just not part of something you care about. You may have a source with manganese and no present treatment. And again, this doesn't delineate between always present, sometimes present, or the level to which manganese is present. You may have a source with manganese all the time or some of the time, but you have a treatment system with limited performance. Or you may have source water with manganese and you have a fully compliant existing treatment system and you can sit back and put your feet up and it's all good. So from a treatment perspective, if you just sort of open up a book, there's an ACWWA pocket field guide on iron and manganese treatment. It'll just list out some forms of treatment and everything is good. Sequestration at the top is not actually treatment. That means not removing manganese, but chemically treating the water so that manganese does not precipitate. So let's just leave it in there. That won't get you a regulatory compliance, but that has been an accepted and marketed method of dealing with manganese. There are still municipalities that deal with what I would call non-compliant treated water, and they avoid customer complaints by sequestering or keeping it from precipitating. Green sand filtration is a trade name applied to a type of process. It's the same as Kleenex. Green sand is a product that represents a type of process. The same as Kleenex is actually a tissue, or whatever you want to call it, but it's a brand name. And there's a whole litany of oxidation conditions for manganese removal, membrane treatment, biological treatment, and I'll just touch on a couple of those. So when I go to Dow presentations, they always throw up these diagrams, and I figure I have to put one in to make a legitimate presentation. So they say that this is supposed to represent what manganese could look like as a function of pH and electrochemical potential. But I consider manganese around three variables when it comes to treatment: pH, retention time, and form of oxidant. The goal in treating manganese is to move manganese from a dissolved form, which is usually what it comes from, if it's in surface water or groundwater, which is this guy in this area over here, and you got to move it from that circle into that circle, where you then get a solid form of manganese. Surface water manganese can be complicated because it does complex with organic matter and other constituents, so it doesn't necessarily behave stoichiometrically like it would if it was just existing in this equilibrium diagram. It can be harder than predicted to remove manganese from surface water because of the way it complexes with organics. That's anecdotal, but it's backed up by some form of science somewhere. From a pH perspective, if you're going to remove manganese, you need high pH. If you are going to remove manganese, you need more retention time. And if you are going to remove manganese, you need the strongest oxidant possible. Air being the weakest, followed by chlorine, permanganate, and ozone. If you really want to remove manganese, you drive all those to the highest you can, and you end up with a very expensive process. So herein lies the dilemma. Manganese has not traditionally been regulated as a health-based parameter. Plants often operate to remove as much as they can, but these three parameters cost money, And the more you want to remove manganese, the more money you're going to spend. And traditionally, that's been money spent on something that does not get you regulatory compliance. It just gets you a little less manganese. So you end up with plants of different arrangements. So I'm going to talk first a little bit about surface water treatment. This is a caption of an existing plant in Nova Scotia with particular provisions for manganese treatment, and this would be the most common of the ways in which manganese is removed from surface water. That's hard to see, but you take raw water, you add a pile of lime to increase the pH, then you add permanganate, and you mix that in a tank, and the manganese oxidizes into a solid particle, and then following that oxidation at a high pH, you inject the water with CO2 to decrease the pH, and then you add coagulant. That's a front-end oxidation process for manganese control in a surface water treatment plant, which is the most common form of manganese control. The problems with doing that are lime costs money, permanganate costs money, additional mixing tanks cost money, and CO2 costs money. And up to that point in your process, you've done nothing other than oxidize manganese. So you've just added a pile of chemical, and you've just gotten manganese on that diagram from a dissolved to a solid state. And then your coagulation process starts. So you go from a natural pH of 6, you go up to pH 10, 11, 12, back down to a pH of 6, and then you add coagulant. There's a bunch of money spent, and you need to build the tankage to do that. Plants in Nova Scotia or in the region, and this is not exhaustive list, but the plants in Halifax, the surface water plants, Moncton, St. John, the New Waterford plant in Cape Breton, and Truro, by examples, are all surface water treatment plants that have specific unit processes for manganese control. So by population, even on surface water, if you look at the population served by surface water in the region, this would represent almost the majority of customers. And I am not sure about some of the Newfoundland ones. I know Windsor Lake does not. The Babel's Big Pond plant in St. John's might, and that's a large plant, but I don't know. So it's very common, and it's only the plant in Lake Major that has pre-filtration chlorine, pre-filter chlorination for oxidation of manganese, which is generally not practiced anymore as a design principle, especially on surface water, because of the likelihood that that would increase disinfection byproducts with contact with organic matter. So you don't highlight it as a technology because you wouldn't normally do that because of concerns around DBPs with what we know now. This is an example of a data set from a plant in Atlantic Canada that has a seasonal manganese problem. Do you have seasonal manganese? It sounds like a commercial for drugs or something. Talk to your doctor about treatment for manganese. Side effects may include. So the raw water manganese, this is old data, it's 10 years old. But this is very representative of what happens. So prior to this point, the manganese is going along flat like this, and this is in-plant operational sampling. And then one day or 1 week, it just starts to go up, and it goes up every day. And that has to do with temperature inversions and fall season and that sort of stuff. And for a while, filtered water quality is good, and then at some point, this process reaches a tipping point where the raw water manganese is too high, and whatever is there as a process can no longer oxidize all that manganese, and it starts to come out in the filtered water. So more than being a regulatory problem, this amount of manganese in filtered water will oxidize into black water within the distribution system and would cause issues. So that area over there is the problem. And so in this particular facility, manganese, once it gets to be 0.3 to 0.4, starts to be more than what the process can handle, which may have to do with the pH or the oxidant dose or the retention time or a combination of those things. Another example, another plant from Atlantic Canada. This data spans over 5 years. And looks kind of cool with the color, but anyway, this is always floating around the traditional guideline of 0.05. And then you see these spikes, and these are more or less annual and are predictable and happen every year in a lot of surface water supplies in this region. There are not that many plants that have a flat line on manganese, or even something that stays above the guideline all the time. There's a lot of this seasonality. Some plants always have a small issue that gets worse, and some places always have a pretty big issue. Truro, I know, has year-round manganese that they have to deal with. I've got a few of these things sort of strung together, which are sort of brief process flow diagrams of how the industry approaches manganese treatment today. But generally, you're talking about a process that is really just part of a larger process. So the thing we looked at before is there's pre-oxidation of manganese using a high pH, something like permanganate to turn it into a particle mixed, and then you start with coagulation. This is an older figure. It says DAF, which could represent any form of clarification, and then filtration. So you remove manganese and iron through the clarification step, and then you remove more from the filtration step. But the point here is that unless this is running correctly, the rest of it can't do anything about it. You either oxidize it up front, or you deal with it in the filtered water, generally speaking. And it's hard. It's a hard metal to oxidize. Iron is very easy. So again, making this work requires generally a high pH, a strong oxidant, permanganate or ozone, and retention time. There are lots of examples of treatment plants where these two tanks are combined, or it's expensive to do that. So you know what? Let's just keep the pH neutral, and let's just add some permanganate to raw water and mix that for a couple of minutes and avoid the high pH, because that costs more money because we have to feed more lime. That is done typically. That reduces the efficacy of that process. You will not oxidize as much manganese at pH 7 as you will at pH 11. I even believe it's exponential or on some sort of nonlinear curve. Alternatively, so far alternative that no one does it, you could do a whole treatment plant and then build another treatment plant after that. And you could have a standard surface water, natural organic matter treatment process. And after that, you do a post-filtration step, specifically to remove manganese. And I wouldn't be surprised if this actually happens. That's why it's up there. I could see this happening within the region in coming years as this guideline is implemented. Some places may have existing processes that are just too hard to retrofit, and you just do a bolt-on solution at the back end of the plant. Similar to the first one, this is just another variation. You replace that clarification filtration step with a membrane filter, but again, you have an oxidation step, and then a coagulation step, and then the membrane filter. But having the right chemicals to make that work is very important. Same sort of thing again. We do a coagulation plant before a membrane system, followed by the media filtration. I'll talk about oxidative media in a second, which is really what I guess we call the green sand process, because green sand is a product. There's a process name on it. Catalytic oxidation or oxidative media would be a generic form of that, which kind of has its basis in groundwater, but can be adapted to a surface water. There are combination membrane systems where there's oxidation. So this sort of thing without the oxidation represents sort of the system there's a few of in Nova Scotia, where there's 2 stages of membrane filtration. That process on its own would not remove a lot of manganese if the source water were high, and you could oxidize before a low pressure membrane and filter that out, or do the 2-stage membrane and then a manganese absorption system from there. In the municipal groundwater side, so that's just a whole string of process options on surface water. Generally, they all focus on front-end oxidation or back-end filtration, adsorption, filtration. So that is sort of in comparison to the groundwater approach to manganese. And groundwater treatment for manganese has been around forever. It's very, very established, but is changing. It hadn't changed for a long time. So the general approach is usually some form of oxidation or combined with coagulation, followed by a filtration system, almost always with pressure filtration. And there's a biological filtration option, which is interesting in this region. Now, these are interesting times for manganese and groundwater in Nova Scotia. There are currently 3 municipal groundwater treatment plants under construction in Nova Scotia that are all going to commission around about the same time as each other. And they are operated or designed on 3 different types of manganese treatment from groundwater. So there are 3 new plants of about the same size treating groundwater for manganese using 3 different technologies. And moreover, I guess, I can't remember my point about that. There's something else about that. The 3 towns are in Pictou and Lewisdale and Pugwash. Oh yeah, the point was, these projects did not come about because Health Canada was contemplating changing the manganese standard. These projects came about because of the traditional issues of acidic water quality and the fact that it's just not cool to provide black water. Pictou has had black water for 60 years, ever since they had to chlorinate, so that's not 60 years, it might be 30 years or so. Lewisdale has had black water since they converted their surface water to groundwater about 20 years ago, and Pugwash just drilled wells 2 years ago, and they're connecting those as part of a project that includes a treatment plant. So I find that really neat as a treatment person, that not very often within a short distance you have 3 municipal plants of 3 different technologies that are all starting at about the same time. There are lots of examples of existing systems besides those ones that are being built that are in the region that have different processes. The largest 2 are the Sydney plant and Fredericton. So if you combine Sydney and Fredericton with that list of surface water plants, you would more or less have every major municipality in the Maritimes, excluding PEI, that has a form of manganese treatment in the plant currently. Not all of those systems are always able to comply with what the new guideline will be. So you see a combination of biological filtration. There's several of these in New Brunswick, and there's a lot more of these. This is just an example. There's probably 20 more municipal systems that have groundwater treatment for manganese. So the chemical oxidation and filtration, which is what was referred to as this oxidative media thing, consists of raw water, which is dosed with some form of an oxidant, followed by a form of media filtration. Now, what has changed from traditional approach is that the old days for manganese removal in groundwater, there would be a pipe, and some would say, where do I feed permanganate? Because this is what you do for manganese, is you feed permanganate and you put it on a green sand. That has changed. It sort of goes like this. This green sand filter is a catalytic oxidative media. It's a manganese dioxide coated filter media. If you dose the raw water with permanganate and you have any amount of retention time, you will start to oxidize manganese from dissolved to solid form. And then when it goes through the filter, it will be removed by size exclusion, which is not the goal of a green sand filter. The goal of a green sand filter is to remove the manganese by having it oxidize on the surface of the media. So the current version of a green sand system includes a pre-dose with chlorine only immediately before the filter vessel. There is no objective to oxidize the manganese before it gets to the media. If you oxidize the manganese before it hits the media, you will probably have some of it break through because it's only oxidized to a very small particle, and then it can just pass right through the filter. You are providing basically an accelerant into the raw water to complete the oxidation on the surface of the media where it adsorbs to that media, and then it's backwashed. So that's a change. The change from permanganate injection with with actual oxidation before a green sand filter. And it seems very slight, but it does make a pretty big difference. And when we started looking at this, I initially questioned, like, everyone was moving away from permanganate. Permanganate is very expensive and it's very hard to access. In a Canadian market, it's not so hard to get. In the United States, it's very restricted because of its use primarily in refining cocaine and heroin. It's one of the primary chemicals necessary to refine hard drugs. Not that I know, but anyway, that's what the internet told me. So we'll move from that to what is a different version. So I'm going through these sort of 3 groundwater systems because they are the basis of the 3 plants that are being done in Nova Scotia, plus all the existing ones. So the first process is your sort of typical traditional approach. This is more of a proprietary arrangement, but has several versions where you take a source water and you inject a coagulant and an oxidant, and you mix that or react that in a tank. Then you dechlorinate and then you filter it to treated water, and the filter will remove the iron and manganese. That's in place in Goose Bay in Labrador and is the basis of the plant for Lewisdale in Cape Breton. So there's coagulation and oxidation before filtration. And a biological process involves addition of air to raw water for some form of ORP control or oxidative state, and filtration through a pressure vessel that includes certain strains of bacteria that help to oxidize / incorporate the manganese into a biofilm layer. And those plants exist. It's principally a proprietary process, but there's several in New Brunswick, and they work very, very well. And that's the basis of the plant for pugwash. That process is about double the capital cost of the other 2 processes. This is an example of a pilot system, which is very rudimentary for a typical kind of green sand type of groundwater system. This little filter vessel contains green sand media and some standard sand, and you hook that up on some wells and just determine what kind of loading rates you can run with and what kind of quality you get from there. This is a biological filtration pilot that we ran a couple of years ago. We ran it with a pre-filter here and different vessels with experimental media. There is ongoing work, I guess, related to biological treatment of manganese. And on the testing and analysis side, this is like an advertisement for Hawk. So I did this because if you've been in a water plant, it's almost guaranteed you've seen one of these 3 devices, its predecessor or current market equivalent. So Hawk more or less owns the spectrophotometer business in water treatment analysis. And most plants rely on an apparatus like these to test in-house for manganese. So what does that tell you? This is something we talk about quite a bit. If you're using the general Hawk process for manganese monitoring in a plant, you are not measuring total and you're not measuring dissolve. You're generally measuring what I call the reactive manganese. There is a Hawk procedure for doing digestion, which most plants do not do. I know there are some that do. And you digest the sample before analyzing it. Typically, the manganese test that's done in-house in a plant is a sample, powder pillow, drop, 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 weight, analyze, you get a number. When you report that number, you're not reporting the same thing that you would be reporting if you did a certified lab test. Not because one's certified and one's not. It's a very different analysis. It's not being done in an ICP or an MS. It's being done using a colorimetric test. And so that creates a problem. You're running a plant, you're doing daily testing with a Hawk method, getting a result and reporting that, and then you send a sample to the lab and it comes back 0.2, 0.3 higher. And when it comes to this change in the standard, for me as sort of the practice doing design work, treatment plants, I can't say that there's any operational impact or design impact to the standard because I don't necessarily believe that this type of instrument is capable of telling you the difference between 0.05, 0.02, and 0.015. If I see a data set from a plant that has 0.03, 0.04, 0.02, you need about 30 or 40 of those days, and you generally say it's probably compliant. But if you record 0.05 or 0.1, 0.015 day to day, I don't really know that the method, combined with the sort of inaccuracies of the test and the operational stuff, is really telling you all that much. The 0.1 limit is a real limit, but moving from 0.05 to 0.02, there's not much you're going to do any differently because of that, because the test method that's going to give you a number quickly doesn't have that good of repeatability on it. So that issue for me is probably the thing that I struggle with the most. You're either going to remove all the manganese you can and you're going to get good numbers, or you're not. It's kind of hard to separate the difference between 0.05 and 0.02 operationally. And that's all that I have. Anybody have any questions?